Hello, everyone. Hope you guys are all doing well. Thank you for the intro. So I am Ekmekji. As mentioned, I'm a senior engineering manager at Rockset. I was supposed to have a co-presenter today, our VP of engineering, Louis Brandy. Unfortunately, he's not feeling well, but I'm still happy to be here to talk with you about the 6 hard parts of running vector search at scale. So let's see how this guy works. No? Cool. Awesome. So we'll go over some very quick intros. We'll talk about the actual 6 hard parts here, and then we'll go into some real-world solutions for how you combat some of these problems when you're running applications at scale. Spoiler alert, I work at Rockset, so we're going to talk about how we've solved some of these problems at Rockset. And then we should still have some time for Q&A at the end. Great. So again, very quick intros. I'm Ari. I'm an engineering manager at Rockset. Been there for the better part of 5 years, starting off in our database team, building out our indexing and query execution engine, and more recently on our teams that own the control plane and ingestion engine. For those of you who don't know, Rockset is a real-time search and analytics database for AI and non-AI applications. And yeah, we get to do some cool stuff that I'm happy to talk about when we get to the real-world solutions. Before that, did some work in ML infra and kind of the AI startup space back in the late 2010s. And before that, even at Facebook, working in the RocksDB team. For those of you who don't know, RocksDB is an open source storage engine founded at Facebook. It powers some of the biggest, highest performance applications in the world nowadays. And where I work now, Rockset, is actually founded by some of the founding members of RocksDB from back when they were at Facebook. Great. Also, this is a vector search talk, so let's just make sure we're all talking about the same thing when we say vectors. What are they and why are they cool? Why do you see so many booths downstairs talking about vector databases? Well, the reason is because vectors are a really great way to give structure to an otherwise relatively unstructured problem. Okay, we use something called an embedding model, right? An embedding model, I'm going to hand wave over this. There's so much to talk about here. It could be many talks, but we're going to assume an embedding model exists, and it takes some unstructured thing like an image, and it takes that and converts it into a fixed size array of numbers, which we'll call a vector. Typically, the sizes for something like this, it can vary based on your model. Let's talk in typically hundreds to thousands of elements. Most recently, for example, the OpenAI ADA 2 model has about 1,500 elements in your embedding. So this is a relatively large thing that's being produced and stored in your vector database. Great. So let's go through these 6 hard problems. Here they are listed out. We'll go one by one, starting with vector search compared to vector database. The tagline here, if you can remember one thing from this first point, is that if you're actually building an application that needs to do vector search, it's going to end up having to solve more database problems than just vector problems. Okay, more database problems than just vector problems. And this is actually really subtle, and if you're not careful, it'll bite you later on when you productionize and scale your applications. And the reason for it is not because database problems are just fundamentally harder or anything like that, right? Both vector problems and database problems are hard, but the practical considerations of running an application at any meaningful scale means that you're going to end up solving many, many such vector problems and database problems, and the database ones will bite you. So we'll go over some of them in a minute. You know, another thing, beware of, it's easy to prototype an application with vector search. It's easy to download something off of Hugging Face or get an API key for OpenAI. But if you're not careful, you'll unknowingly reinvent a database. And some of the things that you might reinvent without realizing it are listed here. We won't I'll gloss over this for now, but the idea is serving things at scale, needing updates to be atomic, needing sharding and replication and query routing and optimization. Again, you'll think that you're just adding one additional feature to your vector search app until you've spent 6 months building what effectively is a query optimizer. And so if you're not careful, you'll end up in this boat. You don't want to do that. Number 2, incremental indexing of vectors. Oh, there should be a graphic there. I don't know why. Anyways, so incremental indexing of vectors. This is actually one of the really hard unsolved problems in vector search today that I don't think people talk about nearly enough. And so the idea is we use indexes and databases to speed up queries. I think we all know this from some point in our education or our career. Vectors have very special kinds of indexes, often graph-based. And one property about them is that they are very difficult to incrementally change. At a certain point in time in your database's lifecycle, you will go and create your vector index. And this vector index will be really good at giving you fast and relevant results for your vector search queries, typically for something like an approximate distance or approximate similarity search. But new data is coming into your database all the time. And what do you do with that? It turns out the ways that you can take a new vector and put it into a vector index to make that vector index kind of reflect the new state of the world with your new data, it's very suboptimal and inefficient to do. To give you some intuition here, this is kind of similar to if you had a binary search tree that was balanced. And in a balanced binary search tree, you get logarithmic lookup time, life is good, operations are fast. But if you're incrementally adding new values one by one into your balanced binary search tree, what's going to happen is it's going to become unbalanced, your lookup times degrade to being linear instead of logarithmic, and things just start not working the way that you want them to. Something very similar, like the moral equivalent of something similar happens here with vector indexes. And so what you'll effectively need to do is periodically do a rebuild. So what do you do if you have this? This is really an important thing just to be aware of. There's no silver bullet solution here. For the first point, it said use an actual database that has these database operations. This one has no silver bullet, but you do have a couple options you can be aware of and things you can choose to do. One is you might just say, forget it. I'm going to embrace the fact that my index is going to get suboptimal, my lookups will get slower, my queries will get slower, or they'll be less accurate, I'll get less recall in my results. Maybe that's okay for you. Maybe based on your application's needs, that works. And periodically you remediate it through something of your own. That's cool, you could do that. Another option is you can do something like this batch indexing approach. In that case, you might say something to the effect of, I will build an index every hour on the hour for the vectors in my database, and in the interim time, I'll just accumulate the new vectors into some other data structure, maybe its own kind of index itself, and I'll have some application logic to combine these two. I'll both query the database that was, or the index that was formed at the hour, and I'll then also query my data structure for stuff that's happened since then. And you could do this. Now, there's a lot of challenges here. Again, you want to use a real database so you can do things like atomically swap that back in and have your query results properly use the right thing, to have multi-version concurrency control so you actually keep the old indexes around as long as a query is running that's referencing them. A lot of hard problems that you can avoid if you use a real database, and then you can go and build some of these approaches. And the third thing you could do, this is in the science category or the innovation category, is you can go and build a new kind of vector index or make some major breakthrough with HNSW or something and go find ways to make it incrementally indexable. If you do, you'll probably win some kind of an award or at least be invited to talk about it, so you should do it and publish it. Great. Next is data latency. Data latency is not talked about as much as it should be. So when we talk about anything that's product-facing, customer-facing, building an experience a customer cares about, you typically want the data there to be fresh. And so data latency is the time it takes from when something enters your system to when it is actually queryable. And so what you'll notice is a lot of systems are built to occasionally bring data into the index, occasionally bring it into the search results. If you're using a system, like a data warehouse, for example, for certain analytics use cases, warehouses typically have like a vacuum operation, like an explicit operation that you have to issue to bring new data into the query results. Right? Now, really, what I'll say here is just you need to understand what your tolerance is here. You might have an application that having data that's 5 minutes stale is perfectly acceptable. There are certain vector search applications and certain recommendation applications. Like if you're building a movie recommendation for a streaming platform, you can probably make a very good recommendation based off of data from my watching 5+ minutes ago. If you're building an e-commerce personalization or recommendation system, probably you actually need to know what I did in the last few minutes, maybe even in the last few seconds. And so understanding what your application's tolerance here is super important so that you can pick a system when you're buying, or maybe design a system if you're building to handle the right kind of data latency. And again, these are fundamentally different architectures. You can't just take a system like a warehouse that's meant to be batched and just increase its, or decrease its iteration time. It's not going to work. You're going to spend a ton of money and still get a suboptimal result. These are fundamentally different. And also be aware if you have any kind of replicated storage in your system, which is true typically if you have like a legacy system that is doing storage-based replication to scale out query serving, you're going to have data lag and data latency in between your replicas as well. Metadata filtering. So this is another hard problem that, again, people don't realize, because when you're doing a lot of low-scale demo or kind of initial development, it doesn't bite you, and then when you get to scale, it bites you. What is metadata filtering? It's super simple. For anyone who's used a database, it's the where clause of your database, right? Here are some examples. I want to see images that are similar, but that have been updated or uploaded in the last 10 minutes. I want to see streams that I might like, but only if the user is online currently. I want to have a recommended product that I might like on your e-commerce store, but only if you still have it in stock. I don't care about out-of-stock products. Right? This is something that any application that serves a real customer use case, you will have some kind of metadata filtering, and having it be efficient and having it be ideally in line with your vector search will universally make your product better and your customers happier. So why is it hard? We talked about indexes before, and we talked about how indexes are important to serve queries quickly. And again, at a certain point in time, you'll build your vector index. Okay? The problem is the vector index is built on all of your vectors, of all of your embeddings that you have. Again, in the product recommendation example, let's say I run a large e-commerce store. I might have 1 million unique products, and I've taken the time to embed each of them into some vector space. I can do approximate similarity search. I can power good recommendations in the general case. But now I have a customer come in, and they want to see products under $50 that have 4 stars or more and that are in stock and that deliver to my house by tomorrow. I do that all the time. And so if you're doing something like that, guess what? I don't care about recommendations across all 1 million products anymore. I care about recommendations maybe across 50,000, 100,000, 10,000, just depending on the filters I've chosen. And now you can no longer really use that index in the same way you would use it before. You have a couple of approaches here, and there's 2 kind of more legacy approaches and 1 kind of more advanced modern approach. So the 2 more legacy ones are what we'd call pre-filter or post-filter. In a pre-filter world, again, using the product recommendations example, first I'd apply these metadata filters. I'd whittle down from my 1 million products down to my 50,000, let's say. And then within this 50,000, I can do more of an exhaustive search. I can compare, the cosine distance or dot product distance or whatever for each of these 50,000 to my target embedding. And I can get back, the top 10 results or whatever I want to show to my product. That's an option. That can work sometimes if your filters are selective enough, and we'll come back to that. Post-filtering is kind of the opposite. Post-filtering is, well, I'll just use my vector index pretending filters don't exist, but I'll request more records from it. Let's say I only want to show 10 actual products in the recommendation. I'll request 50 from my index. And after I get the 50 back, I will apply these metadata filters on top of them. But there's a lot of speculation happening here, right? If I get 50 and I run the filters, I might be left with 20 that meet the filters. I might be left with 2. I might be left with 0. And so you can imagine in this, if you're going to go the post-filter route, you have to build some non-trivial retry and back-off logic to make sure that, if I request 50 but only 2 match, and I have to go request 100 this time, and now only 8 match, and at some point I have to give up and only show 8 recommendations, even though there do exist 10 ideal recommendations to show a customer. So those are, again, more legacy approaches. More modern, ideal, kind of golden approach here is what's called single-stage filtering. And the idea of a single-stage filter is to choose a database where the vector index can be concurrently executed alongside other indexes in the system so that you get a true result that is both ideal from a vector search perspective, but that also meets your metadata filters. We'll talk in a little bit about how we've actually done this at Rockset. But in general, if you can accomplish this, you're going to get better quality recommendations. You're going to actually get the nearest neighbors for your vector embedding. And you're going to also meet the metadata filters so you can provide whatever user experience you want to your application. Very closely related, filter selectivity estimation. Right? So we talked about metadata filters. Let's say we agree that they're important. Okay? Now, what do I do about that? Well, it turns out that metadata filters are pretty abstract, right? I want the 5 nearest neighbors to this vector embedding where blah. And if you're building a real application at scale, typically the filter part is dependent on some user data and some user input and some app data. So what that means is you can't really predict it, right? I actually don't know if, I might choose show me products where the price is under $50, or I might say products that are priced under $10,000. And the difference between those two is extremely different in terms of how many records it's filtering out versus not. This is a really, really well-studied problem. For those of you who know something about databases, this is basically the quintessential heart of cost-based query optimization. And the idea is you want to potentially reorder the filters in the order they're applied so that you get the most selective ones first. including your vector search index. And you want to be able to evaluate them in different ways, push down predicates, and do a lot of things that traditional databases have done for decades at this point, but that vector databases and applications that need vector search sometimes don't realize is a problem that needs to be jointly solved alongside the vector search. Again, if you're dealing with small data sets, you're dealing with small data, you're not operating at scale, this is not going to matter to you. Whether you apply predicate 1 then predicate 2, sure, I got my result back in 15 milliseconds versus in 18 milliseconds. Big deal. If you're running with billions of rows of thousands of queries per second, you're trying to do embeddings across 1,500 or more element vectors across this space, you have indexes that are being updated in real time, this is going to really make the difference for whether your application can serve 10 recommendations a second or 1,000, and whether your results are returning back to a user in half a second or in 10 seconds. And the product experience there for your customers at scale is just vastly different. Great, so let's come over to now the sixth hard problem. In my opinion, this is kind of the most subtle and interesting one. And this is the idea that resources are very finite in any application that you're building. Whether it's on-premises or in the cloud, they're finite to some extent. On-prem, you're really finite. You have to wait for the order to arrive from NVIDIA. If you're in the cloud, you have to wait for new instances to come up and to move over the data. But at a single point in time, you have a finite amount of resources to serve requests, okay? And there's ultimately going to be contention here between the indexing that you're doing when new vectors are coming in, when you're constructing your approximate index, when you're running queries on them, and then you're going to actually contend with the actual queries being run by your application. And at the end of the day, someone's going to lose. Again, at scale, these are coming in at different rates. They change throughout the day based on your customers' workloads, and you can't entirely predict this. And so you're going to have contention, and you have to kind of choose to some extent who's going to lose out. There's two cases actually here. There's a more simple case. In the simple case, let's just view it as one stream of writes coming in and indexes happening, and one stream of personalization queries coming in for your e-commerce application where you're doing vector search. Okay? That's the simple case actually. It's still super hard, and so it's in quotes. But simple case. The harder cases is what happens when I'm running at scale and I have multiple applications running, I have multiple ingestion workloads happening, I have multiple logical clients sending queries even though they're part of the same application, and I can't really control any of these. I want my data latency to be low, I want my index to be up to date, and so I'm periodically, let's say, rebuilding it. I want my queries to be fast, but I can't really have my cake and eat it too. Right? It's super hard. If I have a batch and a streaming ingestion workload here, and I'm trying to index new vectors and pass them into my indexing library and reconstruct the HNSW graph or whatever I'm doing, guess what? If there's a batch workload and a streaming workload, chances are a system that you pick may not be able to give you some quality of service guarantees between these. You might have actually, let's say, a movie recommendation use case running alongside a product recommendation use case, and you want the product recommendations to update in a few seconds and the movies to happen in a few minutes. Guess what happens? When you send the batch of movie update vectors, that one's going to slow down too. You're going to get a bad experience for your customer. Or if you have, again, multiple applications sending queries, they're doing expensive operations. Vector search, by any comparison compared to traditional database operations, is expensive. And so if you're running a lot of vector search queries, all of a sudden, they're going to slow each other down. And you might have certain customers or certain, I should say, applications that you want to give very low latency to, and other ones that you might not care as much. And again, a lot of systems won't natively handle this and give you the ability to give different guarantees here. And so this is something to be mindful of, to know what is the tolerance that you have for this. Again, it's entirely application dependent. You may have the tolerance for this, spikes in your latencies or decreases in your QPS or decreases in the recall of your index because indexing is slow, might be acceptable. But chances are, if you're running at scale, at least one of your applications, at least one of your use cases needs you to give better guarantees here and to do better than just saying, well, I had a lot of indexing happened, I couldn't control it, my queries timed out, and I didn't show you a recommendation in the app. That's not really a great way to handle the situation. Also, I'll mention background jobs. For example, if you are doing a periodic full index rebuild for like a face index or for like an HNSW index, that takes a lot of resources. Vectors are very memory intensive, right? And these resources are constrained. Memory is constrained here. Vector search queries, especially if you're using a graph-based index, vector search queries can be memory intensive. Vector indexing is memory intensive. Something will run out and something will give, something will spill to disk, and you will see it by an order of magnitude change in the runtime of that thing. Cool. So those are the 6 hard problems, right, just to go over, right? You should really pick a vector database. Don't reinvent databases. You're going to be miserable, and your application is going to be subpar. Pick a true database that supports these things. Incremental indexing is unsolved, so just pick which side of the coin you want to be on, how you want to handle this, what's your tolerance for new records affecting the overall structure of the index. If your data distribution isn't changing, it might be okay to leave it and kind of just deal with it. If your data distribution is constantly changing, you probably need to be more clever. Data latency, again, understand your trade-offs and pick a system that is built for the kind of workload that you expect to run. Don't try to take a batch system and use it for more real-time updates. Use a streaming system in that case. But if you don't need that, pick a batch system. It'll probably be cheaper. Metadata filtering universally will make your product better, will make whatever use case you're building better, and whether or not you like it, you have to do it. You don't want to use a separate vector database to do your vector search and a separate other kind of database to do your metadata search, and then have some client-side or application-side logic to join the two. It'll be stale, it'll be a bad experience, it'll be slow. And to do that properly, you need something that can actually properly estimate the selectivities and to push down predicates, to reorder filters, to combine, ideally, the execution of the vector search with the execution of those filters and give you the best performance and the most relevant results. And finally, be aware that things will contend for finite resources like memory in these systems. Cool. So those are the 6 hard problems. Let's talk about how we've solved some of them at Rockset. Unfortunately, don't have time to talk about all of them. So Rockset, for those of you who don't know, we're, again, an online database for search and analytics, for AI applications and other applications. We've added vector search. And so the way we've done it is the following. I should also add that Rockset uses under the hood RocksDB as its storage engine. I mentioned briefly RocksDB out of Facebook, a really high-performance storage engine. And so what we've done here is we actually use FACE, the Facebook AI Similarity Search Library, and specifically we use the inverted file index here. And what this effectively does is if you give it a bunch of vectors, it basically runs k-means. It finds some number of buckets that roughly uniformly partition the vectors into each bucket. The buckets are called cells, and they each have a middle point called the centroid. And so we use FACE to construct this index. And the reason why we use the IVF index, the inverted file index, is because it really nicely complements our search index, which I'll talk about in a minute. But for now, all you need to know is if you add a record into Rockset that has, let's say, a name, an age, a location, and some vector embedding, so I guess this is for like some users table, what we'll do is we'll pass this at indexing time, ingestion time, we'll pass this embedding to the FACE library. FACE will tell us which cell and the corresponding centroid this embedding is closest to, and we'll kind of add some internal fields to your record for the centroid that this belongs to, and the residual, which is basically the distance of this embedding from the centroid of the corresponding record here. Okay? So we map this for every record. And then now let's say you're running a personalization query, a recommendation query, something where you're doing some kind of a vector search. I should also add, it's cool that you can do here vector search in just SQL, and what feels like very natural SQL here. I'm selecting out, let's say, similar user profiles to mine, I guess, and I want to make sure that the location is in the city that I'm in. I'm from LA originally. So I want to find similar users to me, and the similarity is by descending ordering on this approximate dot product, and there's a metadata filter here on the city. Okay? Well, what can we do here? What we do is we take this target embedding, which I guess in this example would be like my user profile embedded into some vector space. We'll pass it to FACE and say, hey, FACE, what are the 3 closest centroids for this vector? 3 is configurable, and you can get higher recall if you pick a bigger value, but typically something like 3 is a good trade-off between recall and query execution time. So FACE will return to us those 3 vectors, and we can actually rewrite the query in this way. So now instead of just selecting users and ordering by this approximate dot product, I can actually rewrite the query to add in, well, a filter on the centroids, because these are the 3 centroids closest to my user vector. And I can order by this residual, which is a pre-computed floating point number. And so now this vector search query has become just a pretty vanilla-looking SQL query, and databases like Rockset are very good at optimizing vanilla-looking SQL queries. And Rockset has an inverted index, along with a columnar and row and range and type other indexes, but for our purposes now, an inverted index, which structurally looks very similar to FACE's IVF index. They're both posting lists, and posting lists are very memory efficient and compute efficient to intersect. And so in a very low memory, high performance way, we can actually return to you the 5 most similar people to your profile, and you get this back extremely efficiently. Data latency. I'll try to gloss over this here, but basically we use RocksDB. It's really write optimized. It uses this thing called an LSM engine where you append records, whether they're writes or updates or deletes, to a log, and you periodically compact it. That combined with the way that we perform the face indexing at ingestion time basically means that you can individually update fields. So I can just update, the age of my user record or the city without affecting the embedding, or I can update the embedding and I'll recalculate the centroid and the residual. And this way, metadata fields are up to date, so I can filter properly for people in my city. And also vector embeddings are up to date. And some awesome combination of RocksDB and work we've done there to optimize the compaction process and work we've done to integrate with face means that new records can be queryable within about hundreds of milliseconds. For our highest performance customers, right around that 100 millisecond number. And again, inline generation of your centroids using face, and then again, depending on your data distribution, you may need to periodically retrain. That's kind of a user decision because it just depends on what your data distribution looks like. But you can do that to increase recall. But if your data distribution isn't changing, you get great data latency. And finally, resource contention. This is just the most grossly negligent slide because this is like 2 years of very difficult engineering work I'm summarizing in like 5 bullet points. Talk to me afterward if you want to know more. I can talk to you for hours about this. But in short, in Rockset, we've separated the storage layer, which is a bunch of storage optimized nodes that hold your data, from the compute layer, which is the thing that runs indexing and queries. And we've even separated the compute from each other, so multiple compute things can talk to the same storage thing. And so you can have this guy running indexing, this guy running queries, this guy holding all the data, and they share it without replicating. And so from a cost perspective, this is great. You don't replicate your data. And again, vectors are big. From a performance standpoint, this is great because you isolate your indexing and query workloads and even multiple query workloads from each other or multiple indexing workloads from each other. And basically, this gives you your control over how you handle resource contention. Again, grossly negligent. Talk to me after if you have questions. Happy to answer them there. But with that, thank you. And happy to take some questions since we have a few minutes. Okay.